be also viewable through YouTube. Before I start picking problems out, I'm going to open it up to you. Do you want me to go through, you had on page 204, 3 to 51, the multiples of 3. Do you have any in particular that you want me to go through before I start picking problems out? Once again, to reiterate what a chain rule is. Okay, when we have a chain rule, when we have a function to an exponent, to take our derivative, we use our exponent rule, drop our exponent by 1, and then chain it by multiplying by the derivative of whatever your function is. So you do not want to take two derivatives at one time. You just apply one set of derivative rules at a time. So we use our exponent, bring it out front, drop our exponent by 1, and then go inside. We don't take the derivative of this. We leave it alone. When you have a trig function, of f of x, or of g of x, when you have a trig function there, you start yourself outside in. So our derivative is the derivative of our trig function, g of x. Whatever the trig function is, we have our derivative, sine, cosine, tangent, secant, cosecant, cotangent, and then we multiply that by the derivative of our function. When we have an e function, we have e to the g of x. Our derivative is a recopy times the derivative of whatever's inside. Any requests before I start picking? We also still have our product rule and quotient rule that we will have to apply. All right, if we just take a look at problem 9, first off, we have f of x. And if you haven't done these, you should be doing them as I go over them. Problem number 9. We have g of x is equal to the square root of 5x plus 1. So first we need to recopy this into something that's workable for us. So we have 5x plus 1 when we deal with the square root. Liam, what exponent do we have to utilize for a square root?
1/2.
1/2. So now we have applied we can now apply our exponent rule with our chain rule. So taking your derivative, our exponent goes out front. Go ahead and move your exponent out front. Rewrite the 5x plus 1. Do not take the derivative of the 5x plus 1. Just rewrite the 5x plus 1. Drop your exponent by 1. So we have 1/2 5x plus 1. Our new exponent's going to be what, Adam?
-1/2.
-1/2. Then we take the derivative of the 5x plus 1, which is what, Bailey?
5.
The value of 5. Now, rewriting this, the negative exponent, we'll drop it down into the bottom. Once again, solutions. Your solutions, we need to put it back into radical form, simplified radical form, and no negative exponents. But the one thing I will not have you do is you will not have to rationalize anything. So we can combine the 5 and the 1/2 there to give me 5 over 5 on top. We have a 2 on the bottom. This will drop down into the bottom. So we have 5x plus 1 to the 1/2 power. And then putting it back into radical form, we have 5 over 2 square root of 5x plus 1. And once again, you do not have to rationalize this. You can leave it alone. If we take a look at problem number 18. Once again, if you did not do this, this is a time to go through these and do these. Number 18, we have x squared plus 1. X squared plus 1 to the 3rd power. And then we have x squared plus 2 to the 6th power. And we calculate the derivative. Now, what we have here is we have multiplication between these two. So if we have multiplication, Dylan, what rule we're going to have to apply because we have multiplication?
The multiplication one.
Yeah, the multiplication one. What's the multiplication one called? It starts with a P.
With a what?
With a P, as in Paul. Oh, what happens when we multiply the answer to 2? The product one. There we go. So we have to apply the product rule. So the product rule is we take the derivative of the first term times the second. Well, when we take the derivative of the first, we have to use our chain rule. So go ahead. And you might want to space this out a little bit more because you're going to need a little bit more room. So take your exponent out front, drop your exponent by 1, and then chain it. When we say we chain it, we are utilizing multiplication. So Nate, when we take the derivative of this term here, we take the derivative of the first term, what do we get? Are you there, Nate?
He said his mic's not working.
His mic's not working. All right. Brandon, use our chain rule. What do we have? What happens to the 3? 3 comes out front. So we have what?
It'll be 3x squared plus 1 squared times 2.
Times 2.
X.
2x. Because because we have to take the derivative of the x squared, which will give us 2x. So that's just the derivative of our first term, and we multiply that to the second. So we still tag along the x squared plus 2 to the 6. And added to, now we take the first times the derivative of the second. So we take our first, which is still the x squared plus 1 cubed, times the derivative of the second. Okay, so apply your chain rule to take the derivative of x squared plus 2 to the 6th power. Carmela, what do you get?
6 times quantity x squared plus 2 to the 5th times 2x.
That is correct. Very good. So now we look to simplify. And this we can look to simplify. Our coefficients that we have here are numbers that are just standing alone. We can multiply together. So we have the 3 and the 2x to give us 6x. X squared plus 1 squared times x squared plus 2 to the 6th. And plus the 6 and the 2x gives us 12x. X squared plus 1 cubed times x squared plus 2 to the 5th. Sorry about that. So there's our final answer. Once again, do not need to oversimplify this. This is fine how it is. You can stand this alone and it's okay. Now some books may sit there and go, okay, I call this oversimplification, but it's something that you could do. If you have to set this equal to 0, you could factor out a greatest common factor of x squared plus 1 squared and x squared plus 2 to the 5th. So you could factor them out. X squared plus 1 squared, x squared plus 2 to the 5th. And then inside of this, you would be left with 6x times x squared plus 2 plus 12x times x squared plus 1. And I guess you could probably take out a 6x also to even bring out a 6x out of both of these. And that would leave us with x squared plus 2 plus 2 times x squared plus 1. And once again, you could simplify that even more within the radical then to give us 3x squared plus 4. But to me, at some point, we apply our derivatives and we go forward from that point. Yes, there's applications as we go further on math where this is going to get set equal to 0 and we can use our multiplication property as 0. Let's take a look at I'm trying to find a quotient rule 1 in there that's I know we didn't have to do it, but we're going to do it. Problem number 29. Once again, we can all work on this together. Problem 29, where we have, I'm going to change it to x. H of x is equal to x squared minus 1 on top to the third power. And on the bottom, we have 2x plus 1 to the fifth power. And we want to take our derivative. Now we have two things that are being divided. Ozzy, what are we going to have to apply now when we have two things that are divided? The what? The quotient rule. That is correct. We have to apply our quotient rule, which is a derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. So take your derivative of your top. Once again, you have to apply your chain rule here. Liam, what do you have?
Three is x squared minus 1.
So what power?
Oh, to the second power.
Times
2x.
2x. So that's the derivative of our top times our bottom. Minus the top. Times the derivative of the bottom. So take your derivative of your bottom. Adam, what do you have for the derivative of the bottom?
Quantity x squared minus 1. Or, 5 times the quantity 2x plus 1 2/4 times quantity x squared minus 1 times 2
Times the value 2. So we have the derivative of the top times the bottom minus the top times the derivative of the bottom. And then we have to put this all over the bottom squared. So we have to square the entire bottom. What that does with our bottom, we have a power to a power. When I have a power to the power, Bailey, what does this turn into on the bottom? 2x plus 1 to the fifth, all to the second power. This turns into what?
2x plus 1 to the fifth times 2x plus 1 to the fifth.
Okay, but if I have to the fifth and to the fifth, what can I do with my exponents there?
Multiply them?
Multiply them. If I have a power to a power, I can multiply them. So I have 5 times 2, which gives us
10.
a value of 10. Now on the top, I can combine once again the 3 and the 2x. Give us 6x, x squared minus 1 squared, times 2x plus 5 to the fifth. And I can combine the 5 and the 2 together to give us 10. X squared minus 1 cubed times 2x plus 1 to the fourth. Now the one last thing to simplify here is if I take a look, I have 5 2x plus, or I'm sorry, that should be a 2x plus 1. I have 5 2x plus 1s here. I have 4 2x plus 1s here, and I have 10 2x plus 1s there. I could take the same factor out of all 3 groups here. I got 3 groups. I got 2 groups on top, and I have 1 group on the bottom. How many 2x plus 1s could we cancel out, Dylan?
4.
4 of them. So these go bye-bye. This gets reduced to 1, and then this gets reduced to 6. So our final solution will be 6x, x squared minus 1 squared, 2x plus 1 minus 10 times x squared minus 1 cubed, all over 2x plus 1 to the 6. And that is our derivative. So once again, we now have the application of chain rule to go with the product and the quotient rule. If we look at 30, last one we'll take a look at. We have the tangent squared of n theta. Now, as I talked about, when we have a trig function to an exponent, what I would suggest that you do is take the exponent on the outside, because what you start programming yourself to do is work yourself outside in with the derivatives. Okay, so when I'm doing my derivatives, I go from the outside element to the inside element. It's opposite to what we normally did with respect to eliminating parentheses. Eliminating parentheses, we always work inside out. When you deal with derivatives, you work yourself outside to in. So taking our derivative, you first deal with the exponent. And bring it out front. And drop your exponent by 1. The next thing we go inside, the next thing we run into is the tangent. So then we have to remember, what is the derivative of tangent? Oh boy. What is the derivative of tangent? Evan, did you ever make it back in here? No Evan today. What is our derivative of tangent? Huh? Evan is here. Hello, Evan. How are we doing today?
He's unmuted, but he can't talk for some reason.
That's okay. That's fine. Just glad to have you here today, Evan. The derivative of tangent is going to be what, Ozzy? Secant? What else goes with the secant? No. The derivative of tangent Anybody? Anybody find it?
Secant squared.
Secant squared, that is correct. So we times it by the secant squared of n theta. And then we go inside of n theta. Well, theta is our variable in this case. So we take the derivative of n theta, which will just be n. Just like having, if I took the derivative of 2x, it would just be 2. The derivative of 5x would just be 5. So the derivative of n theta would just be n. So taking the 2 and the n, we can combine them together. 2n tangent of n theta times the secant squared of n theta. Questions? All right, the first paper in your packet, and I'm pretty sure I also put this on there, so if you weren't here on Wednesday, I posted this on Google Classroom. You can print it off if you want, and once again, if you want to come up here and pick up one of these packets, that is fine. Just tell me. I'll put it on the table out there. And you can pick up a packet. It's all of our notes and all the worksheets already printed out for you. So you do not have to worry about printing them at home and using all the copier ink and then get yelled at by mom and dad because there's no printer ink at that point. So this would save you a step in regards to not having to print additional things out. If you want to come up, once again, just tell me, Carmela, I put yours out there. So if you, whenever you pick up your books, everything is there for you. But if anybody else wants this, just email me or stick around right afterwards and you can tell me. So what you should work on this weekend is the first worksheet in the packet or whatever's posted on Google Classroom. Solutions are also posted on there. Monday we'll come in, we'll go over a few of these. It depends on what we're dealing with respect to time. I may spend a second day on this in regards to the chain rule because it's important that you're able to do these basic functions of derivatives as you go forward and move forward because the functions only get more complicated, but it is a very basic thing in regards to calculus, being able to take a derivative. It's a very fundamental thing that when you go through Calc 1, you can take derivatives. It is a huge part of Calc 1 and what is being discussed with respect to Calculus 1. When you get to Calculus 2, you start dealing with more of the integrals, which is the anti or the undoing of the derivatives. But we'll touch on that in April, hopefully, or March. Questions you have? All right, that's all I have for you today. Wish you were here, but it is what it is. If you have any questions, once again, email me. And if you wanted a packet of information or a packet of worksheets, you can come up here and get them. Just tell me that you'll be coming up, and I get it out there. Other than that, have a good weekend. Stay safe. Stay distance. Hopefully, we can get back to normal here soon. And take care of yourself. Adios. See y'all.
This is Gregory.
Yeah.
Matt, can I please have one of those packets?
Who is this?
Liam Riggenball.
Liam Rickenbaugh. Yes, I will put it out on the table between the two doors outside my room. It will be out there, and you can just drive by, do a drive-by, and pick it up. I'll put your name on it. I'll put a little tag on it, and you can come pick it up.
Okay.
Anybody else?
I think everybody else left.
Huh?
Everybody else left.
Everybody else left. How you doing, Liam? You doing okay?
Yeah.
That's good. That's good. Didn't know you were gonna be off a month, did you?
Uh-uh.
Yeah, me neither. All right, that's good. I'll have it out there for you, Liam.
All right, thank you.
Uh-huh.
Bye.
Yep.